Okay, so this is on, and then Qt is on, sequence containers is on, Vim is on. Yes. Okay. Yes, and then I mean you know how to use the terminal, so it's inside sequence. Sequence. Yeah, your two files are your basic vector and
Cool.
yeah.
Cool. All right.
Okay. Cool. And then
Let's go back to sites.
all right. I think good. And then can you press on that? Get the vectors.
All right, you guys. So we're gonna start off by finishing a bit of what we didn't get to on Tuesday, and then we'll switch over to the new topic, which is gonna be the standard template library, which is something really exciting. But first, to finish up C++ types.
All right, welcome back, everyone. So you thought after 2 lectures of me, you're finally done with me. I'm gonna speak for like 10 more minutes, and then you'll get Anna. Yay! So let's finish up some types. So last time I briefly mentioned about structures, where I briefly talked about this concept of the STD pair. Right? The pair is essentially you can put in 2 different types, and then that allows you to that packs these 2 types into a pair, and you can pass them around, return them as you want. In C++ 17, they have this new feature called structured binding, which is this line over here. That essentially, when you are returning a pair, you can automatically unpack the variables into 2 different variables. At this point, are there any questions? Yes?
Should we use it in 106B?
Avoid using this in 106B, yeah, because some section leaders don't know what STD pair is.
Yeah, this is also a relatively recent feature, so it's not guaranteed that it's using the correct version of C++.
Yeah, let's just say the 106B auto grader uses a pretty old version of C++. So avoid using this in 106B. Yes, question?
Can that syntax be applied to custom structs?
That's a very good question, which is my very next slide. Let's keep this going of your questions predicting what's coming next. All right. So, any other questions? Yes.
Can you do something similar to like a vector?
So you mean like when I return a vector, can you like immediately unpack?
Return a vector and unpack.
Yes, you can do that as well. You have to be careful about that. When you return something, you have to make sure that that you are unpacking it into like the correct number of elements. Yeah, this is most commonly used for pairs. By the way, there's a pair. There's also a thing called a tuple, which is essentially it's a pair, but you can have as many things as you want. Okay. Any questions so far? All right. So let me briefly talk about a struct. So if you look at this program right now, returning a pair is pretty nice. You can return 2 things at once. What is one disadvantage you can see from this code? Yeah.
You only return 2 things, but how the number of elements you're limited to just is not 2.
Okay, sure. So yeah, this program can only return 2 things, right? Because we're using a pair right now. You can extend it to a tuple if necessary. But then you mentioned a good point, which is the pair itself. One thing you know is there's 2 ints in it, but how do you know the first one is a min, the second one is a max? Right? Whoever's reading your function can say, oh, you're returning 2 ints. It must be the first one's a max, the second one's a min. Right? There's no like self-documenting way to say, oh, which one's the min, which one's the max. So perhaps a better way to do this is to use a thing called a struct. A struct it's a more general form of a pair or a tuple in that each component that you give, they can be of different types, and you can give them as many different types as you want. In addition, the components inside your struct are named, which means when you're referring to different parts in your struct, you can refer to them by name. So for example, for a struct here, I can name the 2 components min and max. so that later on when I want to access a min or a max, I can call, okay, what's the min of this struct? What's the max of this struct? I saw a question over here. Yeah, question.
So, sorry, in a pair or tuple, all the types must be the same?
I think I misspoke. The types don't have to be the same. Yeah, in a pair or a tuple, they don't have to be the same. And when we do go deeper into the STL next week, you'll often see that the STL libraries return a pair, and then the pair is usually a Boolean and also something else. Okay. I think find, which is like a pretty common function you'll use, it returns a Boolean and something else. The Boolean represents whether or not something was actually found, and if that Boolean is true, then the other component is the actual thing you found. If nothing is found, then it's false and some random junk. Okay, good question. Any other questions? Yes, question.
Is a struct like slower in the way than using a different data type, or are there any performance issues, I guess, with these different data types when you're using the same job?
I don't. I think pair and structs they work in the same way. I'm not super sure, but I think a pair under the hood might be implemented as a struct. So I don't think there's a huge issue. Do you know the answer?
A little more lightweight than a struct, I think.
Okay.
Because, it doesn't require being stored anywhere in memory.
Yeah.
But speed-wise, it
Yeah, should be similar. Structs are a very old construct. This is not a modern C++ thing. If you program in C, you will see structs a lot. Yeah, so structs are actually borrowed from C. Now, if you've programmed in Java or Python, you'll notice that this is really kind of similar to what a class is. Right? A class, you can have instance variables and then you can refer to each of these instance variables. This is kind of like that, except a struct, everything is public. So you can immediately access the min or the max of any struct object you create. Right? Structs work exactly like objects. Question, yeah?
When you're accessing, are you accessing the reference to the variable, or are you accessing a copy of that?
You're accessing a reference to the variable, yeah. So as an example, let's over here. So here we're using a struct price range instead, where the price range has two components, a min and a max. Right? And then you can see over here, we can access the min and max fields of a price range by saying p.min and p.max. Okay. If you wanted to change p.min, you can say p.min equals something, and because it's a reference, it's like actually changing what's inside p. Question, yeah.
So you mean we cannot do the encapsulation in struct?
Structured binding? Encapsulation as in like private variables hiding. Mm-hmm. Yeah.
You can do that?
I don't think you can say the word private. Yeah, but a struct is a very lightweight form of a class. Yeah. If you're taking 106B right now, classes will be covered halfway through the quarter. Mm-hmm.
And structs were actually the reason sort of why C++ was created, because the creator of C++ was working with C with structs and got so tired of working only with public numbers that he decided to make C++ a bigger language.
Mm-hmm. Any other questions? All right, and then you can do the same thing with the structured bindings. You can when you return the struct, you can access the variables and extract them out into separate variables, kind of like what we did for the pair. All right, let's not go through this example. Okay, so for example, another struct we can do, I was going to do this example, but we ran out of time, is we can write a struct called course. And inside the course, there can be like a string code, CS106L. There can be a start time and an end time. Time is another struct that we can create later, which has like an hour and a minute. So for example, the start time could be 3:30, end time could be 4:30. The struct can also have a vector of strings, instructors, and an Avery. All right. Yeah. So structs work in the same. This is just another example of how you can work with structs. You can have a vector of courses, itself a struct. I will go through these later if we have time. The last topic I want to briefly mention is initialization. So in other languages, initialization is not a big problem. But in C++, apparently, I just searched this up. There are like 26 different ways you can initialize a variable. And then here's a little meme, or here's a little GIF, which is about how many ways you can initialize. All right, and then I don't know 2/3 of these.
That's good.
Are we done yet? And there we go. Okay, we're done. Okay, yeah. So essentially, there's a lot of ways to initialize, and it's not really feasible to know or memorize all of them. The way to initialize also depends on what type you're working with. So, ironically, to fix this problem, C++ decides to add one more way to initialize. All right, so there's a 27th way to initialize called uniform initialization, which is supposed to fix all of these initialization problems. Okay, so a lot of the structs that you work, a lot of the objects you work with right now, they themselves have a special constructor called the initializer list constructor, which allows you to initialize something by giving it like a list of parameters. So for example, by default, structs like course, we can initialize them by putting different components of what we want inside our course inside these curly braces. And that will initialize our course with the course code CS106L with a time 3:30 and 4:30, and with a vector of instructors, me and Anna. A couple questions. Yes, first question.
The second parameter, 1530, that's supposed to be a time struct. You don't need to say time. You don't need to explicitly tell that it's a time object or a time struct.
Good question. So notice that we never mentioned that the 1530, the blue thing here, is a time. And the reason for that is because when C++ sees your course struct, it sees the order in which you're putting them. It's a string, then a time, then a time, then a vector. So, okay, so it goes to your initializer list, which is this over here. This is not an initializer list, but it goes into here and it says, okay, the first one, treat that as a string. The second one, treat that as a time. And then to create a time, we can do another like uniform initialization. It's gonna say, okay, the first part is the hour, the second part is the minute. And the same thing for everything else. It treats the third thing like, okay, that has to be a vector, so convert that to a vector of strings. Okay, good question. Yes?
Can you change the components of the course now, later on?
Can you change, oh, are you saying like, can I say now dot course code equals something? Like changing it?
CS106B instead of like you rewrite it.
Yeah, so what this does is it just initializes a course, which starts with these values. You can now go in and say now.code equals CS106B. Yeah, good question. Other questions? Yes.
So uniform is just doing it all at once?
Uniform is this way of initialization works for a lot of different things, not just structs.
Sorry, could you explain like more? I still don't get what uniform initialization is. What's so special about it?
Yeah. So for example, initializing a vector. This way to initialize a vector creates a vector with those elements. Okay. Now vectors in courses, they're like different kinds of things, but there's one generic way to initialize all sorts of different objects. So for like, if you notice here, we're initializing a lot of different kinds of objects. Like this is a time struct, this is a string, this is a vector, but they can all be initialized in the same way using the curly braces.
Oh, okay.
Yeah. Question, yeah.
Is that how you do OOP in C++?
Is
Using struct to...
Oh, so OOP is a topic, object-oriented programming is a topic we'll actually cover later in this quarter. Structs are sort of like the predecessor of OOP in C++ almost. But C++ has its own version of like classes and things like that. So it's not just structs. Yeah.
All right. Yeah. And then if you look on the in the first lecture I mentioned that vector has a ton of constructors. One of the constructors you'll see is this initializer list, and what that does is it takes this initializer list that you give it, and it and that's the constructor that's being called. Question, yeah.
You can pass a struct as a reference, by reference,
Yeah.
and then change specific values within that struct.
Yeah, so the question was, can you pass structs by reference? The answer is yes. They work kind of like objects, except everything is public. All right. Yeah. So when you use the uniform initialization, it prefers to call a constructor which has an initializer list. So here, if you use that for 3, what it does is it creates a vector with the element 3. If you prefer to call the other constructors, you have to use the more normal, like, okay, let's pass in 3. If you look on the STL specification for a vector, passing in a single number represents the size, the initial size. So what it does is it creates a vector of size 3 with default values 0, 0, 0. Question, yeah?
Wait, but I thought Journey might have said that like when you initialize it with size 3, it doesn't automatically default to 0, 0, 0, 0. Isn't it just garbage, garbage, garbage?
So that's actually a tricky question. So the question is basically around does C++ automatically 0 initialize the objects that you create? It turns out that's actually a trickier question, or a trickier question than one might initially assume. Sort of the consensus that we could find was that C++ 0 initializing, you can count on C++ 0 initializing when it's a global variable or some variable. There's like certain keywords that indicate that it will automatically be null initialized, but in general, it's true that you shouldn't count if it's solely a local variable on an object being null initialized.
Yeah, that's a good question. Because I think that there's a constructor here which says the default value is the default value for a certain one. Yeah, for ints. Is there default value for ints? Does it just give it 0?
Oh, yeah, all primitives are also automatically null.
Okay. Yeah. So I think here it has a default value. So if you don't give it a default value, then it just says, okay, you have a count, and its default value is going to be 0 or something like that. Okay. Yeah. All right. So now you know one small piece of what this whole mess means. You know what this means, the initializer list, and you also know what a reference is. And then we'll cover everything else over the course of the quarter. Question, yeah.
So would we have to make our own course method with an initializer list?
Yes. Well, so by default, if you don't give it the initializer list, what it does is it just instantiates each parameter to it follows the order in which you declared each variable. So the order we did it in was a string, the course code, then 2 times, and then a vector. So then it just matches each one to the different members. Yes?
So if you define just a new course without specifying any parameters, that means will 0 initialize every one of its parameters, or the equivalent 0 initialize? Okay.
Does it? For ints, though, does it do that for ints?
I believe it definitely does it for ints. We would have to check if the 0 initializes a vector or things like that.
Yeah.
Like the time, yeah.
Okay.
But you could definitely just create it and then later set the values. You don't necessarily have to set the values when you are creating.
Okay.
All right. And there we go.
Awesome.
All right.
Good job,
Hey, everyone.
Avery.
So I'll be taking a break for a week and a half.
Resting his voice. He's done a worthy job. All right, so there's a couple things that we want to get to today. Before we jump into our new topic, though, one thing that we wanted to emphasize over the topics that we just taught you guys, specifically, for example, string stream. It's something that a lot of people haven't actually heard of. And we saw you a couple of cool things that you can do with it. However, one thing that we also want to emphasize in this course is not only showing what unique tools does C++ have, but also teaching you guys or reminding you guys to always think about, okay, I have all these different tools. I also need to remember when do I use each of them. So we just taught you string streams, but we want to emphasize that it's not necessarily now a replacement for the string everywhere in your code. Some things that a string stream is good for, these 3 applications in particular. So say you want to process strings in your code, for example, that right there is like a path in your file directory. No worries if you're not familiar with it right now. You'll see it soon in 107 or even 106X or B, I believe. If you want to simplify that to its shorter version, for example, formatting input and output strings. So we didn't get a chance to talk about string manipulators in relation to input and output streams or string streams, but things like endl or flush, those are all known as string manipulators. And so are things like uppercase and hex. And so what these do is, for example, if you are outputting your string, you can insert the string manipulator uppercase and it'll output everything as uppercase. So for things like that, where you want to format the strings that you're working with in particular ways, string streams are also amazing.
Just to jump in, there are slides at the end of the slide deck right now about manipulators.
Yeah.
So if you're ever curious, feel free to look at those.
Yeah, so if we have time today, we'll hopefully get to those, and if not, they're on the slide deck for you guys. The last thing, for example, of course, the string to integer that we worked with. In other words, when we're dealing with different types in our strings, that's another good use case for string streams. On the other hand, for example, if in your program you are just concatenating strings, it turns out you really don't need a string stream. It's this extra functionality that you're not really using, whereas your good old friend string.append is actually the best thing that you could use there. So it's just a reminder that like this is a super powerful tool. Just remember remember that a string, for example, is also there for a reason. All right. So the other thing that we wanted to do before we jumped in to our new topic is survey results. Thank you everyone for filling out the survey. I have no idea why you would do that without some sort of motivation. No, I'm just kidding. So a couple of things just for you guys to let you know. This is what the class looks like. It's a pretty even spread among different classes. A lot of freshmen, but we also have a good number of sophomores and graduate students. So that's awesome to hear, and it helps us a lot because it lets us know that we're really dealing with a wide range of backgrounds. And similarly to that, our majors are, of course, computer science, but also ranging across a wide list of other ones and many more than that. And then finally, in case you guys are interested, this is why you're sitting in this classroom with us today. You want to learn C++ as it's used in industry. You want more practice with C++ as a language. You want to supplement 106B and X, which is a super valid case. And then specific applications. And so for those of you who are taking the class because you want to learn how to apply C++ to specific like work that you're doing or other applications, we won't necessarily cover those directly in class, but we do encourage you to come talk to us at office hours, which we will be releasing with the assignments tomorrow or today. And then that way we can also just talk to you about specific things that you guys are interested in. So won't necessarily cover this, but we will try and focus on these 3 applications to make the class useful to you guys. Cool. So this is exciting. So what you guys have learned so far are streams and C++ types and a bunch of other really cool, interesting new building blocks of the C++ library. If you recall, this was the map that Avery made for us at the beginning of the quarter. Now what we're doing is we're taking a step back. And we're actually going back to one of the first things that was created in C++, which is the standard template library up in that upper right-hand corner. And this came out really, this wasn't a built-in feature of C++. It wasn't there in 1972 or I hope I got the year right, when C++ was first created, but in the very first wide release of C++, the standard template library was one of the first things that was built into the language. And we will soon see why. So for today, we're going to be focusing on a couple different things. So before I get to that, I think this is a nice summary of the standard template library. As mathematicians, try to lift theorems into their most general settings. This guy, Alex Stepanov, wanted to lift algorithms and data structures into the most general version of themselves. So again, instead of every programmer having to write their own implementation of like a find or sort algorithm, this guy wanted to bring it into one standard library that people could work on and make more efficient in one source base. And that's sort of something that we take for granted now, but back then, definitely a new feature. So for this lecture, we're going to be covering 2 parts of the standard template library, containers and adapters. And those words seem pretty unfamiliar, but you'll find you guys actually know most of what's already there. So that'll be good. And then over the next 5 or so lectures, we'll be diving into these 3 other core parts of the STL, iterators, algorithms, and functors and lambdas. And really, these 3 things are the reason why so many people, or why rather we, when advertising this class to you, said that C++ is magic. And I'll give you guys a hint of that right now. But yeah, once we get into those 3 lectures, you'll really see how powerful the standard template library is. And I promise that you will be amazed. There's also a couple other things in the STL, but there's sort of more minor concepts that we won't be covering in this class.
I just want to add one thing. Even though the STL is one of the oldest libraries in C++, it is constantly evolving. If you
That
go
is
on the
true.
documentation right now, you can see there are like dates, which is like, oh, since C++ 14, since C++ 17. They're adding more and more features, which are supplementing the new language features of C++. All right, so don't think this is a super old library that no one uses. It's everyone in C++ uses these, and it's getting more and more sophisticated.
Yeah, that's absolutely true. Yes, back there.
I've been told that like this is updated by volunteers.
Say that one more time.
The STL is updated by volunteers, like people who make it better.
Yeah, that's a great.
How do people kind of like get to that point of like, do they just kind of like email because, oh yeah, I want to work there? Or, like, what are they doing?
Yeah, that's a
Can I
great
say
question. Yeah, okay, everyone's.
So they have this C++ conference, which is held by. It happens very, very frequently. You can actually see their meeting minutes online, and it's there where they vote on essentially like what new features to add into C++, and discuss like what are the problems in C++ right now, how do we fix them. Yeah, volunteers, and that's one of the. You bring up a good point about volunteers. This is a good important point about C++, which is unlike some of the other languages like Java, C++ is not owned by like a specific corporation or industry.
Open
right?
source.
Java is owned by
Oracle.
Oracle, yeah.
Yeah.
Yeah. So unlike those, C++ can be used anywhere. If you want to use it in your business, there's no licensing issues.
Exactly, and that's honestly that's been a core feature of C++'s development as well. Because it's open source, people have been writing extensions to the language. There's a set of libraries called the Boost libraries that are also they're sort of like the STL++. They're like an extension of the STL that also provide a lot of unique functionality. So I forget if we're covering Boost libraries, but just to show that C++ is super extensible is one of its big features, and part of that is because it's open source. So to give you guys a hint of where you guys will be 5 lectures from now, here's an example of what this STL can do. Other way.
There we go.
All right. Okay, so if we go into STL preview, okay, so this is some code that I wrote to do some simple functionality. Don't worry about the details, but essentially, these 3 things are what this code is doing. It's generating n random numbers and putting them into a vector. It's sorting the numbers using some random sorting algorithm, in this case, bubble sort, and then finally printing them out. And you'll notice that if you guys have written sort of programs doing similar things, like this might look sort of familiar. Like you're using a for loop to iterate over all of the spaces in the vector to fill them up. And then don't mind the bubble sort, that's just this particular implementation of sorting, but if you have implemented sorting, that would be one of the ones that you've done. And then again, to print out the vector, a vector doesn't come with an inbuilt string, a .toString function. And so the way that you would have to see out it would be, iterate over one element in the vector at a time. Okay, so let's see if that works. So we're going to, build that. Perfect. So it looks like what our program did was generate 20 random numbers and then output them in sorted order. So if you remember what you just saw in that program, all of this, we are now going to condense that into 5 lines and see what happens. So again, we are going from that into this. And let's see what happens. Oops, let me. Exact same thing. So really, what this is really doing is it's using algorithms and pre-built functions in the standard template library to transform the way that we usually write code into something that's just super simple. So anyways, that's just a hint of what you guys are going to be able to do over the course of the next couple lectures. One other thing that I want to emphasize is that you might also be, wondering like, okay, since I'm condensing it into sort of these other functions, like, is that somehow slower or something? Because now you're not just like who knows what's going on under them? as it turns out, one other benefit of the STL is that because it's been the standard library for C++, people have worked on making the implementations of all of these functions the most efficient possible. So even if you did want to rewrite one of these functions, like the generate function that you might have seen yourself, it may not actually be as efficient as this STL version.
Can I add one more thing?
Yes.
Can you give me the code over there?
Yes.
So, the code, yeah. So, if you look at the previous implementation, this is a very like mechanical way of writing the code, right? You're actually going through the elements one at a time. You're moving them around. You're printing them all one by one. But if you look at what the STL library does, like just looking at the code, you can maybe not like perfectly tell what it's doing, but you can kind of guess what it's doing, right? It's okay. You create a vector, you generate a bunch of numbers, you're sorting them, and then we're copying them into something to do with cout. All right. We're moving from a very mechanical, like very low level process to being able to harness these algorithms that we're given and to solve problems by focusing on like the larger problems instead of moving numbers around mechanically. So that's also one benefit of the STL.
Yeah, and while we are on this love fest for the STL, one other benefit that we'll give you guys a preview of is that it turns out if we wanted to, we could completely replace this vector of ints with, say, a stack or some random object that we define ourselves. One of the biggest benefits of the STL is that it is generalizable. This exact function will work on any other data structure that satisfies certain conditions. But anyways, this is just a preview of the STL. We will be going into more details into all of this over the next couple lectures. But it's to give you an example, to give you guys an understanding of why we are spending the time on this. Cool. So again, that is where we are going. And another quote by our fave, Alex Stepanov. One of, again, C++'s goals, striving for efficiency, and it really helps us understand our problems. Yes?
Did you have to put anything like up the header or something to be able to access those functions? Or is there
Yeah, absolutely. So these functions in particular come in a header known as algorithm, but we will also be we will be going into algorithms in full depth in another lecture, and yeah, we will show you that there. Awesome. So before we can get to all sorts of that cool stuff, we want to also focus on the sequence containers, associative containers, and adapters. So bear with me because a lot of this might actually be really familiar to you. So what I'm going to want to do is emphasize how the C++ version of these familiar objects differ from the things that you guys already have seen in CS106B and X. So a sequence container is actually just a data structure that provides access to sequences of elements. So sequence containers are a subset of containers, which are one aspect of the STL. Containers are really just any objects that store collections of other data. A sequence container is one particular type of container where the data is sequential. For example, you might be very familiar with a vector from 106B or X that just covered it recently. And then these are actually the other four sequence containers that the STL defines. We won't be going into these bottom two, but we will be covering the first two. Okay, so the C++ vector is actually very similar to what you're familiar with if you've taken 106B or X. A vector, again, representing a sequence of elements of any type. And again, a vector can be a vector of any type of object, whether it's an int, a string, a struct, as Avery just taught us about, or even a vector of other types of containers. So, okay, actually, before I go on to this next slide, one thing I want to emphasize is that the C++ vector has a lot more functions in it than the Stanford one necessarily has. So we're providing this nice spreadsheet on the next page so that you can really get a feel for how the vector that you've worked with at Stanford differs from the C++ one, but know that there's even more to our vector than is on the page. So don't get worried about how much text is on the screen. We're actually mainly just putting this here so that you have a reference in the slides if you ever want to go back. A couple of the differences that we want to highlight. Whereas with the Stanford vector, you are to add an element to the vector, you call v.addk. In the standard vector, the similar function is called pushback. And you'll find that that sort of pushback, push front, pop back is something you'll see with the other standard C++ data structures. Another one we want to emphasize for differences, to retrieve an element from a vector in Stanford, you use the .getI function or the bracket notation. With C++, with standard C++, the corollary to get is at, but the brackets also have a slight difference in them, and we'll get to that shortly. Finally, similarly, instead of get, it's at to store values into the vector. Before I go on, are there any questions at this point? Yeah,
I guess just in general, do you know why in BNX we're supposed to use the Stanford libraries?
Yeah, so the question is why in BNX are we using the Stanford libraries? So it actually, it makes a lot of sense on the part of the instructors, because the goal of classes like 106B and X, and even A, is to teach you general design principles of C++, or concepts like recursion that you guys will be learning later this quarter, where they don't want you to get bogged down by language specifics, and so they provide instead like a smaller but much cleaner interface for the C++ language than standard C++, which is, of course, a wild, wild, wild west.
I'll add 2 more things. One thing is to correctly use the STL library, you have to understand iterators, which Anna will cover in the very next lecture. I'll first say the next lecture I think is the single most important one of CS106L about iterators.
In case you didn't hear that, the next lecture is the single most important lecture of
yeah, and we won't be recording it. All right.
We probably will.
So so to understand iterators, you'll have to understand iterators to be able to fully use the STL correctly. So iterators will easily take a week to teach, which is what we are doing.
Right.
So, and then when 106B you only have 10 weeks, you don't have a week to cover iterators. The other concern, sorry, I had one more concern. The STL, following the, and I will talk about this, but following the philosophy of C++ is if you do C++ trusts that you will do everything correctly. If you do something wrong, C++ is very unforgiving. The STL library is very unforgiving if you do something incorrect.
And
so, yes.
That's actually a perfect lead-in, because we will see an example of that right now. How are we doing on time? Oh, wait, okay. All right, so I mentioned that there was one key difference, which was this bracket notation for, or rather, more generally, getting and replacing elements in the vector. So let's see that really quickly, why. Oops. All right, so the main thing that you want to see here is, I'm actually going to delete that. All right, so I've already written a function that just prints the vector for us. You'll notice I'm not using the nice algorithm that we used before. It's just for one, to show you another way to do it, and second, because we haven't talked about it yet. So we're sticking to our old ways for now. And you'll notice my use of the auto keyword that Avery just taught. So once again, if we want to create a vector, let's call it vec. And then actually here, I'll show you. So again, just like the Stanford library, instead of add, we use pushback. Let's make this our names. Yes, thank you. Thank you very much. Cool, and then if we wanted to, we could print that out. But before we do that, I also just want to show that, okay, if I wanted to, we can also see out vec dot get 0. So what is at the current vector location? 0. So I'm just going to change that to right.
Names.
It is names. Actually, yeah, okay. Thank you. Oh my gosh, I tricked myself out. Actually, this was a instructors say this a lot, but yeah, that was a pop quiz, you guys. Good job catching it.
We throw you candy at this point if we were some other instructors.
Oops. Awesome. Awesome. So we see, again, push back and get, at work exactly as we expect. Okay, so now one question that we might have is, what happens if we try and do at an index that doesn't have anything in it? So if you've tried this at all with in 106B or X, then you'll know that what it throws is something called an array index out of bounds exception. So let's try that with this. Let's use names.at2, which shouldn't exist because there should only be indexes 0 and 1. Oh my gosh. In the program at the moment. Okay, so it turns out when we use the at function, standard C++ does a pretty similar thing to what the Stanford libraries do. We get an out of range exception, and if we want, we could catch that exception and do other things with that later. The one big difference that we want to emphasize, and which trips a lot of people up when switching from Stanford to standard especially, is that notice that there are two ways to access and store things in a vector. In the Stanford libraries, you can use either names.get or just names bracket notation. In C++, both of those notations still work, names.at and names bracket, but there's one key difference that doesn't exist in the Stanford libraries. So if we try to do names2, and then just to make sure, we can be like, hello, I've reached this point. It turns out that C++ does exactly what Avery was talking about before. Rather than throwing an exception, which the Stanford library does when you've gone out of bounds, that was not supposed to happen. Give me one more second.
That's correct. It printed the like some empty thing.
Yeah. Actually, here. We'll be extra careful. All right, so I'll go back and debug this later, but essentially what's supposed to happen is that in the standard C++ library, the names bracket notation does not check whether you are out of bounds, and in fact, even worse, it fails silently. So sort of similar to what you guys saw with something earlier in Avery's stream lecture, it doesn't let you know that something's gone wrong. And even in this case, you'll notice that it actually didn't let you know that, in fact, it wasn't an element of that vector. And I actually have a suspicion of why this one worked. But yes, did you have a question?
Would you not get a segmentation fault for out of bounds memory?
That's a great question. So would you not get something called a segmentation fault if you're reaching out of bounds? I believe what may have happened here is that, so not necessarily. The segmentation fault would happen if you're accessing protected memory, but in some cases, since it's a local variable, for example, it may be that that memory is in fact free. So you're just getting trash, rather. But yes, I will go back and debug that, but take away from that. Key difference, when you're using the bracket notation in standard C++, know that you must check for whether it's in bounds first, because C++ won't tell you that for you. All right, so one question I want to ask you guys, why doesn't the std vector bounds check by default? Does anyone have a quick guess to throw in? Yes, in the back.
Because if you write it out well and you are like checking for that, or if you're sizing your stuff correctly, then you won't have to check for where.
Exactly. That's exactly right. Exactly. So again, just reiterating the fact that C++ really will not hold your hand, which is great when you want to do really specific things because you can work with it a lot and do much more with it than any other language, but bad because it won't tell you when you've done that wrong. So yeah, back to the philosophy. Yes?
What happens if you use bracket notation to set the 400th element of the vector? Like, what will it do with the middle parts of it?
Yeah, great question. So it turns out that the way it's implemented under the hood, it won't actually be checking the middle at all.
Okay.
All it'll do is, and you'll learn more about this sort of in 107 maybe, is like it'll basically add 400 from the start and then just check that 400th element or set it.
So when you iterate through, will it just skip all of them?
So if you iterated through, that would be another issue because you're trying to iterate through a vector that is not longer than 2. So you would be iterating through trash,
Okay.
essentially. Yeah. Last question, and then I'll move
So
on.
does that mean that the bracket notation is faster to run?
No one, or actually Avery, do you have?
I think the answer is yes. I mean, because if you think about what the bounds check is doing, it's really like an if statement.
Yeah, okay, that's true.
Mm-hmm.
So yeah, the bracket notation will have one less if statement. It won't be, essentially it won't be throwing the error, whereas
If you're
the
careful
dot
with
add,
your code, you should just use
bracket notation. Yeah, exactly.
Yeah. In most C++ code, you will never see anyone use dot add.
Yeah, that's actually a great point. Yeah, awesome. Okay, so one last thing with vectors. One thing that I believe Cynthia covered in 106b was this idea of adding an element to the front of a vector. And as it turns out, the problem with that is still a problem in C++ standard vectors. So can someone tell me, what is the issue with trying to add an element to the front of a vector as opposed to the back? Does anyone know? Let's do the front.
Then you have to shift all the elements that are after it.
Exactly. So what he said was you have to shift all of the elements that are after. And so we can see that in action. If we want to try and move 7 up, we just had to shift all the elements back before doing that. And so, yeah, that's really not what we want to do.
No.
So as it turns out, also that's a great movie. I think, yeah, if you haven't watched it, Zootopia is great. So as it turns out, C++ has also anticipated this and has actually built another data structure that a lot of people haven't heard of. Oh, sorry. Well, before we do that, again, okay, we want to emphasize the fact of when you use each thing. A vector, you'll find, is almost always a correct thing to use because a vector is just, it's so basic that it's very fast, lightweight, like easy to use. However, sometimes we do want this additional ability to push front. And so, back to my spiel, C++ has actually invented this structure called a deck. So a deck, pronounced deck, is a double-ended queue. Essentially, it's just a vector with this added ability to push to the front in an efficient way. So it can actually push to the front of a vector in constant time, if that term makes sense to you. I'm actually going to skip how a deck works, but feel free to look at the slides afterwards. Essentially, it's an array of other fixed size array, and that's how it's able to not have to shift every element around. But yeah, I would recommend going back to the slides to look. You don't actually need to know how it's implemented under the hood to use it. It's just sort of interesting.
In CS 106b, you'll learn more about that like week 6 or week 7.
Oh, do they?
Yeah.
Okay.
Yeah.
Yeah, so
Yeah.
that's kind of cool. They now introduced the deck.
Sometimes it appears on exams.
Ah, okay, that's interesting. So you guys are getting a sneak peek. So, okay, so in that description of a deck that I just told you, that it's essentially a vector, but with the added functionality of being able to push front in a really efficient manner. A natural question that I might get is like, why would we ever use a vector then? And as it turns out, as in life, everything is a trade-off. So in trade-off for that additional speed, a deck is not as quick as a vector in accessing elements in the vector. So doing things like names bracket I is not as quick with a deck as it is in a vector. So yes, actually, I think this is sort of cool. So I am going to show you guys this example. So this is really just to drive home the point of like the differing advantages of the vector and deck by showing timings. So we can actually, I got you. I'm going to do insertion speed.
Okay. Click here. Click here. Click here. Yeah, and then change it to.
Oh, I
yeah,
see.
there, and then press run.
Yes. All right. And we also wanted to do this to sort of show you guys that we are in fact using Qt Creator. Command line is sort of lightweight, but. All right, so what this code is doing is it's inserting basically 1,000,000 elements or so into a vector and comparing the speed that it takes to push back versus push front. And you can see the purple line is push front and that green line is push back. So you can see from that the difference in speeds with which a vector implements push back versus push front. So that's sort of just an indication that, oh, okay, in fact, maybe we do want something that specifically focuses on making push front faster. And so if we try and do the deck,
Yeah, and then press run.
yes. Awesome. Once again, just inserting basically a million elements into a deck and comparing pushback versus push front. You'll notice that first you'll notice that the y-axis is super small. Whereas the other one had a y-axis of up to, I think it was like 400 or something. This one does both push back and push front up to the scale of 20. So it's almost like 200 times faster. Yeah.
What's the unit on the y-axis?
Yeah, great question. The unit on the y-axis is milliseconds. Yeah. Yeah.
For the vector one, I guess, like, why isn't it perfectly linear, I guess?
Like why did it exponentially grow?
I mean, it wasn't even exponential, it was like kind of piecewise, different linear functions.
Got you.
Because you have to iterate over like every single one, right? So shouldn't it just go as the number of elements?
So sort of the question is like, why did the graph look the way it did? I would have to look at the graph again, but my assumption was that the graph was exponential because as the number of elements increases, with each push front, you have to push more elements back each time. And so the time it should take should increase as the number of elements grows.
Quadratic, right? Exponential quadratic. That's fine.
Exponential quadratic, yeah,
Okay,
same idea. Yes, okay, so this is again showing us, okay, the deck is doing what it's supposed to do. It does both push back and push front super quickly. And then finally, in our conversation of timings, why is it that we don't just use a deck all the time? Well, it's because if we try, what this program is gonna do is it's gonna compare the vector and deck in accessing elements of the vector or deck. So in this case, we will soon see. You can already see how much longer it's going to take, and I can tell you already that the reason it's taking long is because of the deck. So once again, we have a vector, and this program is timing how long it takes to read the value from each index of that vector or deck. Oh, I see. Sorry, you guys. I actually thought it went to the 5 for some reason. So after this, I'll let you guys go, and I'll probably take some time out of my time on Monday to just cover the last couple things.
Yeah. A reminder, the next lecture is probably the most important lecture of the entire quarter.
Yeah, so one more time. In this case, you can see we're on the order of 1500, and the deck is a lot slower than the vector accessing. So the takeaway from this, that should be your takeaway. Use the vector by default. Use a deck when you really are only working with the front or the end of your data structure. Awesome.
Questions outside.
Questions outside, and assignment has just been released on the website. Good luck, you guys.
Can I ask you a really brief question?
Yeah, go for
So
it.
I just came for first time today, and I added it on Access. Besides for reviewing the previous lectures and going up and adding myself to Piazza, is that it?
Can I start
Oh,
preparing
yes,
for
yes,
my
you
class?
can. Yeah, sorry about that. Say that again.
Questions outside.
Besides for adding myself on Piazza and looking over the lectures, is there anything else I need to do?
That's a great question. You should be set. And in fact, the assignment should rely solely on what is covered in lecture. So
Let's go.
yeah.
Oh, do you guys have to go?
No,
we have to go
on that
outside.
side, but we don't want to take the class to the next
Do you
one.
have any? Do you guys have any good links to like the theory behind that implementation?